EEE EC 201 Electrical Circuits 1. Introduction to Magnetic Circuits. In today's lecture, we will study about magnetic fields, flux density, permeability, reluctance, Ohm's law for magnetic circuits, magnetizing force, hysteresis, Ampere's circuital law, determination of flux and magnetomotive force. Introduction. There is a great deal of similarity between the analysis of electric circuits and magnetic circuits. The magnetic flux of magnetic circuits has properties very similar to the current of electric circuits. It has a direction and a closed path. The magnitude of the established flux is a direct function of the applied magnetomotive force, resulting in a duality with electric circuits, where the resulting current is a function of the magnitude of the applied voltage. The flux established is also inversely related to the structural opposition of the magnetic path in the same way the current in a network is inversely related to the resistance of the network. All of these similarities are used throughout the analysis to clarify the approach. Before we study about magnetic circuits, we need to get familiarized with few terms. Now, the flux density is basically defined by the expression B equals phi by A. The flux density defines the number of magnetic flux lines per unit area. The unit for the flux lines is Weber per meter square or Teslas, T. The number of flux lines which will be established depends on the applied magnetomotive force. The magnetomotive force is directly related to the number of turns and current of the magnetizing coil and is defined by the expression F equals Ni. The level of magnetic flux established in a ferromagnetic core is a direction function of the permeability of the material. Ferromagnetic material have high level of permeability, while non-magnetic materials such as air and wood have very low levels. The ratio of the permeability of the material to that of air is called relative permeability and is defined by mu r equals mu divided by mu naught, where mu naught equals 4 pi into 10 to the power minus 7 Weber per ampere meter. Reluctance. The resistance of a material to the flow of charge is determined by the equation resistance equals resistivity into length divided by area, and the unit is ohms. The reluctance of a material to the setting up of magnetic flux lines is determined by the expression reluctance R equals L divided by mu A, and the unit is ampere turn per Weber. Ohm's law for magnetic circuits. Recall the equation effect equals cause by opposition, that is I equals V by R for electrical circuits. For magnetic circuits, the effect desired is the flux phi. The cause is the magnetomotive force MMF represented by this symbol, which is the external force or pressure required to set up the magnetic flux lines phi within the magnetic material. The opposition to the setting up of the flux phi is the reluctance R. Hence, if we substitute, we have phi equals F by R. Although there is a great deal of similarity between electric and magnetic circuits, you must understand that the flux phi is not a flow variable, such as current in an electric circuit. Magnetic flux is established in the core through the alteration of the atomic structure of the core due to external pressure and is not a measure of the flow of some charged particles through the core. Magnetizing force. The magnetomotive force per unit length is called the magnetizing force, represented by the symbol H. In equation form, H equals F by L. So, if we consider this diagram, over here, F can be determined using the value of N and I. That is, F is equals Ni. And the magnetomotive force will establish flux lines phi through this object. The mean length of this object is L, which is 0.2 meter. Hence, the magnetizing force H equals Ni by L. For the magnetic circuit in the given figure, if Ni equals to 40 ampere turns and L equals to 0.2 meter, then magnetizing force H will be 200 ampere turns per meter. In other words, the result indicates that there are 200 ampere turns of pressure per meter to establish flux in the core. Note that the direction of the flux can be determined by placing fingers of your right hand in the direction of the current around the core and noting the direction of the thumb. It is interesting to realize the magnetizing force H is independent of the type of the core material. It is determined solely by number of turns, the current, and the mean length of the core. The applied magnetizing force H has a pronounced effect on the resulting permeability of a magnetic material. As the magnetizing force increases, the permeability rises to a maximum and then drops to a minimum. This is shown in the figure in the next slide. The flux density and the magnetizing force, that is, magnetic field strength B and the magnetizing force H, are related by the following equation. B equals mu H. This figure shows the relation between permeability and magnetizing force H for three different materials: sheet steel, cast steel, and cast iron. These three materials can be used to design the core. In all the three cases, that is, in all three materials, it has been found that on increasing the magnetizing force H, the permeability of these materials increases. That is, they reach a peak value. But in all three cases, it's also found that after a certain value, the graph will decay and will reach a minimum point. A graph of B against H is known as hysteresis curve or BH curve. The BH curve is specific to a given material. In this figure, there are three hysteresis curves for three different materials. One for sheet steel, one for cast steel, and the other one for cast iron. When we solve problems of magnetic circuits, we will be using the BH curve in each and every problem. Ampere's circuital law. If we apply the cos analogy to Kirchhoff's voltage law, that is summation of the voltages around a closed loop must be equal to 0, we obtain the following for magnetic circuits. That is, summation of F will be equal to 0, which in other words state that the algebraic sum of the rises and drops of the MMF around a closed loop of a magnetic circuit is equal to 0. That is, the sum of the rises in MMF equals the sum of the drops in MMF around a closed loop. Thus, F equals Ni. The equation for MMF drop across a portion of a magnetic circuit can be found by applying the relationships, that is, for electric circuits, V equals IR, resulting in the following for magnetic circuits. F equals phi times reluctance. Over here, phi is the flux passing through a section of the magnetic circuit and R is the reluctance of that section. The reluctance, however, is not calculated in the analysis of magnetic circuits. A more practical equation for the MMF drop is F equals HL, where H is the magnetizing force on a section of a magnetic circuit and L is the length of the section. Applying Ampere's circuital law. Now, consider this electromagnet over here. It is composed of 3 different materials: iron, steel and cobalt. So, according to Ampere's circuital law, summation of MMF for a given electromagnet must be equal to 0. In other words, the rise in MMF must be equal to the drop. The rise in MMF is represented by the product of Ni, and the drop in MMF is represented in magnetic circuits by the product of H and L. Now, in this particular electromagnet, 3 different materials are used. Therefore, the product of H and L will be different for each of these materials. Applying Ampere's circuital law, we can say that Ni, the rise in MMF, minus HAB-LB, which is the drop in MMF for steel, minus HBC times LBC, the drop due to cobalt, and minus HCA-LCA, the drop due to iron. Summation of all these will be equal to 0. In other words, the rise in MMF will be equal to the summation of all the MMF drops. Flux phi. If we continue to apply the relationships described in the previous section to Kirchhoff's current law, we find that the sum of the fluxes entering a junction is equal to the sum of the fluxes leaving a junction. That is, for the circuit given over here, if we consider junction A, phi A will be equal to phi B plus phi C, and at junction B, phi B plus phi C will be equal to phi A, both of which are equivalent.